hopefully access it at some point.
Yeah. So by April 15th, I think we should be finished. There's some PhD students also who are attending the course from ICER or not really?
Yeah, I'm not sure. I actually, in forwarded this thing to everybody. I don't know if
I see. Actually, it reminds me I should put my phone on do not disturb. 1 second. Yeah, okay, great. So we can start whenever. Yeah, sure. No problem here. Yeah. Fine. Fine.
Yeah, good evening, sir.
Good evening.
I'm
Hello, sorry, it got. I'm not able to hear.
Yeah, we're not.
I'm audible.
Yeah, now you're audible. Yeah.
Yeah, okay. So then maybe I take the video off. Yeah, okay.
Yeah, I think we cannot hear you.
2002. Hello, am I audible? Okay, so welcome everyone. Sorry for the disturbance. Welcome everyone, and today we have Dr. Suvrat Raju from International Center for Theoretical Sciences in Bangalore, and he works in the field of quantum. He works in the field of quantum field theories and black holes and quantum gravity. He obtained his degree from St. Stephen's College and then continues his PhD in Harvard. And now after working in Harish Chandra Research Institute for several years, now he is a faculty member at the ICTS Bengaluru, and he has been delivering TED Talks and many other events, and has been active in various other forms, and he also calls himself as an activist. And today we are also very happy to have you here, sir. Thank you for accepting our invitation and being here with us. And we also thanks Dr. Bindusar Saro for helping us in arranging this talk. And we also welcome everyone for the talk. Over to you, sir.
Okay, so thank you very much for inviting me to give this talk. I'm glad so many of you have joined. I thought I would talk about, I was asked to speak about the information paradox and its resolution. What I'm going to try and do in this talk is give you a broad overview of some of the developments in the information paradox in the past few years or so, and I'll try and tell you in what sense we think we understand things better and what are the things that need to be understood better. I aim this talk roughly at a level of an undergraduate physics audience, and so I try to aim it so we'd start from something basic and then go on to more advanced stuff. But feel free to interrupt if you don't understand something and ask questions, and we can take it from there. Okay, great. So this is a talk about the information paradox, but the information paradox is really something that emerges when one starts thinking about quantum gravity. So before we talk about quantum gravity, it's important. I wanted to start just by talking about something very basic, which we all understand and learn, and I'm sure all of you would never have been at ICER if you hadn't studied this a lot, and that is just Newtonian gravity. And I'll tell you why this is relevant. We'll come back to this at the end. But in some sense, we started understanding gravity quantitatively and well with the advent of Newtonian gravity. And Newtonian gravity was developed so that we could understand the motion of planetary objects. And so in this case, you might have the sun and you might have the Earth, and people wanted to understand how the Earth goes around in an orbit around the sun. And there was a quantitative law that was discovered for the force with which the sun attracts the Earth. And the law is, as we all know, that the force is given by the product of the masses divided by the inverse square of the distance. And there's a constant that's called the Newton's constant that appears in that force law. So this is a law that we know and we understand very well. And even though it's a very simple law, even though we learn this in school, it's actually a very powerful law. When we talk about science and we talk about the philosophy of science and we talk about theories in science, the Newtonian gravity is a quintessential example of a successful physical law. This is the kind of law that, even though it was developed a long time back and was used, was developed to understand the motion of planets around the sun, it can also be used to understand how a rocket behaves if a rocket is launched from the Earth. If you wanted to understand, as you can see on the right side, the behavior of how the moon goes around the Earth, you can use the same law to understand how the moon goes around the Earth. And if you think about it, you will see that that's something that's pretty surprising. In many areas of science, you do not usually have laws which are valid for large ranges of scales. This is a law which is valid for a very large variety of scales. It's a law that describes what will happen to us if we jump up and down, what happens to a ball if you throw it up. It also describes, what happens to planets as they go around the sun. So it's really valid for a large, even though it was developed to understand one particular system, it's valid for a very large variety of systems. And that's a pretty remarkable law. And even the corrections that we have now discovered and which I'll describe now are, from a quantitative perspective, pretty small corrections. Okay? And so this is a very successful law, and even though it's very simple, it should not be underestimated. But nevertheless, even though it's a very successful law, people realized sometime back that there is maybe about 100 years back, or a little bit more than 100 years back, 115 years back, that there are some unusual aspects of this law. And one example, one fun way to understand why the law is unusual is to think of the following thought experiment. Okay? Think of the following possibility. So let's say there was a giant who came and who pushed the sun. Or let's say there was some alien spaceship which came and fired some rockets and moved the sun from where it was currently. Right? So let's say something like this happened and the sun moved from where it was. The question that one could ask is, when would we know? So there's a sun which is setting outside my window. And the question one could ask is, let's say something was to happen to disturb the position of the sun. The question is, when would the Earth know that the sun has moved? How long would it take for the Earth to know that the sun has moved? So, of course, we know it would take light 8 minutes to come. But Newtonian gravity gives us an answer if we take Newtonian gravity seriously. And the answer is as follows. Newtonian gravity tells us that the force between the Earth and the sun is proportional to the inverse square of the distance between them. And therefore, if the sun moves, the inverse square of the distance between them changes. And because the inverse square of the distance between them changes, this would suggest that we would know immediately when the sun has moved. So if you believe the Newtonian gravity, or you take it really seriously, this is, of course, the kind of situation that doesn't occur all the time. And so, But if you were to take Newtonian gravity very seriously and push it to its limits, this is where we start seeing where a theory might break down. If you push it to its limits, if you push Newtonian gravity to its limits, you will see it makes this prediction, which is that information would travel instantaneously. And this is it's a manifestation of the fact that the Newtonian theory has what's called non-locality. So it's a non-local theory. It's not a local theory. It's a non-local theory because it suggests that you have these forces which act instantaneously at a distance. Now, people realized from many other aspects of physics and from studying the behavior of light and many other things that, in fact, this is something which was not consistent with other physical principles. So from the work of Lorentz and Poincaré and in the end, some final steps taken by Einstein, people developed the theory of special relativity. And the theory of special relativity tells us, among other things, that information cannot travel faster than the speed of light. And therefore, the Newtonian theory of gravity cannot be exactly correct if what we understand about relativity is correct. Because the Newtonian theory, as I just explained, suggests that information would be transmitted immediately, whereas relativity tells us that that's not something that's physically feasible. And so people started to develop a theory of gravity that would be consistent with relativity. And there were other observations about gravity that went into that effort of developing this theory. And the theory that came out of it was called the theory of general relativity, on which Einstein did a fair amount of work. And the final equations, though, were first written down by Hilbert, you see on the left. And they developed a theory that looks very different from the Newtonian theory. The Newtonian theory says that there's some force between two objects, and the force is proportional to the product of the masses and the inverse square of the distance. But general relativity, the equations of general relativity are very different. And the way you should understand the equations of general relativity, for those of you who are familiar with it, you'll recognize these equations. But one way to understand this in words is that general relativity doesn't talk in terms of forces. It says that matter tells space-time how to curve, and space-time in turn tells matter how to move. So sometimes, one good way to think about this is in terms of thinking of the fabric of space-time. So if you go back to the system that I had at the beginning, where there was the sun and the earth, you will see that we have the sun here, and the way you should understand the interaction between the sun and the earth is that the sun causes, both the sun and the earth live on this fabric of space-time, and the sun causes this fabric of space-time to bend in a certain way, as this cartoon here shows. And the reason the earth goes around the sun is not because the earth feels a force, but rather because the orbit of the earth, the trajectory that the earth takes, is the natural trajectory to take in this bent space-time. So the earth follows what's called a geodesic in this bent space-time, in this curved space-time. And so you see that the language that we are now using to describe the interaction of the earth and the sun is very different from the language we had earlier. However, I should emphasize that from a quantitative point of view, the differences between the Newtonian theory and the general theory of relativity are very small. The fact that if you were to compute the orbit of the earth using general relativity, you would find effects which are very small compared to other perturbations on the orbit of the earth caused by the gravitational pull of other planets and so on. And so you would find that the orbit of the earth was almost exactly the same as you computed using the Newtonian theory. But if you think in terms of the language that is being used, or the ontology of the theory, what are the words and the concepts that the theory uses to describe the physics, then you will see that that's a very different ontology. So the ontology is in terms of this fabric of space-time and the sun and the earth both living in this fabric, and not in terms of forces. By the way, general relativity does give you pretty different predictions if you go back and start asking extreme questions. So if you go back to the question that we had earlier, where we had this our friendly giant who moves the sun. Now general relativity will give you a different answer, a very different answer from the Newtonian theory. It will say that if this giant were to come and move the sun, as you see here, what would happen is that you would form ripples in space-time, and these ripples in space-time would propagate at the speed of light, and therefore it would take 8 minutes for these ripples in space-time to propagate from the sun to the earth. And so you see, this is now a theory which is consistent with the fact that information cannot travel faster than the speed of light. And so general relativity is an example of what's called a local theory. In general relativity, everything interacts with something right next to it. So the sun bends the fabric here, and if you were to push the sun, the fabric here would bend slightly differently, and that would in turn influence the fabric of space-time a little bit further off, and that in turn would influence the fabric of space-time a little bit further off. And therefore, information would travel in a local way through this medium, if you like, which is gravitational waves, and it would therefore, travel from the sun to the earth in a finite amount of time and not instantaneously. Okay, so keep this in mind because we'll come back to this at the end of the talk. Okay, but this is one way in which general relativity differs from the Newtonian theory. Now, after people discovered general relativity, they began to try and understand it more and in more detail. And one of the things they found was, of course, it gives us different solutions for planets and gives us corrections, and people verified experimentally the general theory of relativity. But then they found that, you could also find solutions which were very different and, were not like anything that the Newtonian theory gave you. And one such example of a solution is what is called the Schwarzschild solution, found by the German mathematician Schwarzschild. And for those of you who are familiar with metrics and line elements, this is the solution, and it's an exact solution to the equations that I showed you before. This is a solution for the metric, and it gives you, some tensors of the kind that I showed you before. But the point is that you can find some exact solutions to the equations of motion. Now, rather than taking you through the equations, let me just try and tell you a little bit what the qualitative properties of this solution are. So the solution that was found by Schwarzschild has the property that if you're very far away from r equal to 0, so you're very far away, somewhere here in this red region where you can see my mouse pointing, then the solution looks a lot like ordinary space. So it looks a lot like space around us. And then as you start coming in closer and closer, at some point, which in the solution, which is r is equal to twice gm over c square, which is called the Schwarzschild radius, you find that you get what's called an event horizon, which has the property that once an object enters the event horizon, it is not possible for the object to return to ordinary space again. So if you see where my mouse is, once an object reaches inside there, it's not possible for the object to return back to ordinary space, which is far away at infinity. And this object, the solution also has another property. It has what's called a singularity, which is at r equal to 0, which is depicted in my cartoon here as this point at r equal to 0. In fact, in this talk, we'll mostly only talk about the horizon and not about the singularity. Now, when these solutions were first discovered, people thought, well, fine, there are some solutions, and you can often find solutions to theories and to equations, and maybe these solutions are never realized in nature. But of course, over the past many years, we have realized that that's not the case. And these black holes actually exist and they kind of surround us everywhere. In fact, the Nobel Prize last year was given for understanding that there is a black hole, a supermassive black hole at the center of our own galaxy, which is 4 million times as massive as the sun. So it was given to Ghez and Genzel, and also to Penrose, but we'll see Penrose's contribution later, and which is very far away from us. But this is a black hole, so it really, in some sense, realizes not quite the solution I showed you, but a generalization of the solution that I showed you right now. This is not the only black hole. There are many other black holes. Some of them are even bigger. For example, this is a picture by the Hubble Space Telescope of a black hole which is much further away and 500 million times as massive as the sun. Not all black holes have to be millions of times as massive as the sun. This is a black hole whose properties were studied, in fact, when I was a PhD student. This black hole is a black hole which again is in our galaxy, and it's only 14 times as massive as the sun. And it has a pretty interesting property. It has the property that its horizon is spinning so fast that it's almost going at the speed of light. So this is, it's not quite there, but it's almost going at the speed of light. And this is what's sometimes called a near extremal black hole. It's almost extremal. And by extremal, that means that its horizon is spinning almost as fast as it possibly could spin. And by some naming conventions of astronomers, the obscure naming conventions, it's called GRS 1915. But in any case, this is a black hole which is depicted here in the inset here. Okay. Now, of course, as you also know, we not only see black holes from the electromagnetic radiation that comes from around black holes. There is also the emission of gravity waves that takes place when black holes collide. And we have in the past few years also started to see these gravity waves. This is an example. This is a picture of the LIGO detector, and this has opened up a new spectrum, a new way to probe black holes and understand their properties. Now, the question of how you see these black holes, some of you might even be wondering that given that these are black holes, how do you see them? And of course, you don't directly see the black hole. You see things from around the black hole. The black hole modifies space and time around it. And it's by that that you actually manage to see the black hole and study its properties. And that is a very interesting, that's a very interesting topic. And my colleagues at ICTS and other places in ICER also, spend a lot of time studying how to experimentally observe these black holes and how to understand their properties. And that's an entirely, an entire research field in itself. The kinds of things that I'm going to talk about are what are sometimes called vanilla black holes, or what I call vanilla black holes at least. So vanilla black holes are black holes which don't have any of these stars and accretion disks around them, and so they don't emit all these. They don't participate in all of these violent phenomena. And what the kinds of questions which theorists like me like to think about are what happens if you take a black hole and you have a star, and the star just lives in splendid isolation, almost splendid isolation. We'll perturb the star a little bit. Let's say you just think about the star and forget about everything around it. The star is kind of undisturbed. And if the star is massive enough, this kind of a star will collapse to form a black hole and form at late times a solution very much like the idealized Schwarzschild solution that I showed you. And this is a cartoon of what will happen if you take a star which is massive enough, or a ball of dust which is massive enough. It will start off at some large size, and then under its own gravitational force, it will start contracting. And eventually, when the ball of dust becomes smaller than its Schwarzschild radius, which is the dashed line that you see here, then nothing can stop it from contracting. While it is larger than the Schwarzschild radius, there is a chance that some forces might come and might stop it from contracting further. Once it becomes smaller than its own Schwarzschild radius, it will just continue contracting forever till it just contracts into the singularity. And so this is a cartoon, a time slice cartoon of what will happen. Now, in fact, it's not convenient to draw cartoons of this kind where you keep showing snapshots. For those of you who have studied special relativity, you know that it's convenient often to depict these kinds of processes by means of a space-time diagram. So what you see on the left-hand side right now is a space-time diagram where time runs on the y-axis. So the y-axis is not a physical spatial direction, it's a time direction. And in this is the same process that I showed you on the previous slide, now showed in a space-time diagram. And so, you had a ball of dust that at some point was rather big, which is at time t, some negative time or time t equal to 0. And then the ball of dust becomes smaller and smaller, which you see happening here, and then it shrinks to the singularity. And at the same time, this event horizon that I told you forms, this is the purple line, and this event horizon forms and later starts sitting at r equal to 2gm by c squared, as I showed you previously. There are many Indian physicists who were part of understanding these processes. A.K. Rai Chaudhary and P.C. Vaidya, who helped to understand this process. And in fact, this collapse itself is often called, this process of collapse is sometimes called Oppenheimer-Schneider collapse for the people who studied it. But in fact, a Bengali physicist named B. Dutt studied it 2 years before them. So it should really be called Dutt-Oppenheimer-Schneider collapse. But in any case, this is the physics of something that we think we understand. Well, in this physics, as I said, there are no accretion disks, there are no other black holes to collide with it. And I'm going to try and tell you how even this very simple process is interesting and leads to paradoxes. So this is yet another picture of the process that I showed you. This is what's called a Penrose diagram. And the idea of Penrose was, you want to understand in a black hole often what parts are causally connected to another part. In that, as we said at the beginning, there was the fact that information could not travel faster than the speed of light. So you often want to understand when black holes form, from where to where can information travel. So the point of these diagrams which were invented by Penrose is pretty simple. It is just to rescale space and time in such a way that light rays always go at 45 degrees. So rather than this diagram that I showed you previously, where you had a horizon and as I explained in the beginning, if you had some object which is where my mouse is right now inside the horizon, it cannot communicate with something outside the horizon. But from this diagram, it's not clear why that's a property of this region, but but it's not a property of this region. Here, an object here can communicate with an object here. And this Penrose diagram kind of makes it clear. And in this Penrose diagram, light rays go exactly at 45 degrees. And so you see that something which is behind the horizon cannot communicate with something that's outside the horizon, because if you emit a light ray from here, that also goes at 45 degrees. And the only way for something inside to communicate with something outside would be to go at an angle that's larger than 45 degrees to the y-axis. And that is not possible because nothing can travel faster than light. So these kinds of diagrams are called Penrose diagrams. Once again, time runs on the y-axis and space runs on the x-axis. And the only thing that we have done is we have rescaled time and space in such a way that light rays always travel at 45 degrees. Okay, great. So now, as I said, theorists are interested in studying these black holes, but we are interested in now doing a little bit more. We studied the process of black hole formation. After you study the process of black hole formation, we can do a few more thought experiments, and I'll explain the significance of them in a minute. You see, so here's our friendly giant is back. Our giant assistant is back to help us do our thought experiments. So one kind of thought experiment you could do is you could take this black hole, which I show on the slide, and then you could say, what if after the black hole has formed, at late time, somebody goes and throws in some additional matter into the black hole. So what if somebody goes and pushes in some additional stuff into the black hole? So this giant is now throwing in some additional stuff, and it's going to measure for us what are the processes, how does the black hole change when something like this happens. So it turns out, so this is a picture of the same thing shown in the Penrose diagram without the giant now. So you have a black hole, and in addition to the black hole, I'm now throwing in some stuff. This additional stuff is depicted by this orange line. So you see it starts far outside the black hole, and then it goes inside the black hole. Of course, you can guess that any matter which is thrown into the black hole ends up in the singularity, which is here, the red curved line. And the horizon, the black hole grows a bit because it's eaten up a little bit more. And so its mass is larger. And I remember I said the Schwarzschild radius is at a position which is proportional to the mass. And so now it's going to grow a little bit. But in fact, you can describe this whole thing more quantitatively. And physicists in the 1970s studying this found how they could understand this process. And they found, in fact, that in processes of this kind, the way the black hole growed and the way it responded to the way it grew and the way it responded to these kinds of perturbations, in fact, could be encapsulated in a set of simple laws that are now called the laws of black hole thermodynamics. And the reason they're called the laws of black hole thermodynamics is that these laws tell us that if you take a black hole of the kind I showed you and you perturb it, then the mass changes because you threw in some amount, that's this dm, and it turns out that the area also changes, and the mass and the area change in a particular way. The change is proportional to kappa or 8 pi, because kappa is something called the surface gravity, but it's some constant. And in addition, if the black hole has angular momentum and you try and change its velocity by throwing in something that has angular momentum, you will get additional terms which are work terms of precisely the kind that you get in thermodynamics. So if you have a system in thermodynamics which has some angular momentum and some angular velocity, or maybe it has a charge and some potential, and you try and throw in some stuff into that, or you try and modify the system, then you will find that the change in the internal energy of the system goes in this way. It goes like T times the change in the entropy plus work terms, and that the way in which the black hole responds to perturbations is very similar to the way in which thermodynamic systems respond to perturbations. And moreover, it's not just the first law, there is also a second law of black hole thermodynamics, but just like there is a second law of thermodynamics. So the second law of thermodynamics tells you if you take some isolated system, its entropy can only grow. The second law of black hole thermodynamics tells you that the area of a black hole can only grow. In fact, there are these surprising processes called Penrose processes, whereby sometimes you can decrease the energy of a black hole. So you can actually pull out some energy from a black hole, but there is nothing you can do that can or nothing classically that you can do that can ever decrease the area of a black hole. So there's a second law. So just like the entropy doesn't decrease, the area of a black hole doesn't decrease, at least classically. Now, when these laws were first discovered, people thought that maybe this is an example of, or some people thought that this is an example of what we often see in physics, which is that the same equations have the same solutions. I'm sure many of you have read the Feynman lectures, and you know that Feynman keeps saying this many times in his lectures. he says, the same equations have the same solutions, and many times in physics, we find situations where you have different physical systems which are actually described by the same equation. So you might have a mass and a spring, and that's described by the same equations as an inductor and a capacitor. And that doesn't mean the mass on a spring is an inductor and a capacitor, but it so happens that both those equations are just simple harmonic equations of motion. So maybe people could have thought that black holes obey the same equations as thermodynamics, but that's just the kind of coincidence that happens in some other situations as well. So this is what I just showed you. Black holes happen. You have black holes on the left, and maybe the T that I have in front of me right now on the right, and the T obeys some laws of thermodynamics. It has some temperature. It's been getting cold for some time, and the black hole has some laws of black hole dynamics. And maybe these things just obey the same laws, and that's just an analogy, and there's nothing deeper to it. In fact, one of the things that Stephen Hawking showed, which is best known for, is that the fact that the black holes obey the laws of thermodynamics is not just some formal story. It's not just the fact that these same equations have the same solutions, but rather black holes really have a temperature. And one kind of imprecise way to say it, but not so imprecise way to say it, is that if you think of quantum effects, they cause the black hole actually to start emitting radiation with a temperature that is given by 1 over the mass of the black hole. Okay? And so black holes really have a temperature in that if you're far away, you're an observer far away, you will see a stream of radiation emerging from the black hole exactly as a stream of radiation emerges from any other hot body. And the way Hawking explained this process was that he said that if you think of this Penrose diagram of the black hole, near the horizon you might have, due to quantum vacuum fluctuations, pair creation happening at the horizon, and of this pair creation that happens, one particle could go out to infinity and the other particle would fall into the singularity. So if you were an observer sitting far away, you would just see a stream of particles coming through, and that would look like, and he was able to calculate the spectrum of that, and that's what he showed was, a given that spectrum was the same as that of a black body with the temperature that I showed you previously. Okay, so this was Hawking's discovery, and it told us that we should really take black hole thermodynamics seriously and not just as a formal analogy. Okay, great. So if you take Hawking radiation into account, you find that the picture that you have of a black hole is now modified again. So it's not the picture that I showed you previously, but rather a picture that you see now, where at the horizon, there is some emission of light that is coming. And so, there is a horizon, but the horizon is not entirely black. In fact, the black hole is emitting some stuff. This is a highly exaggerated thing. In fact, realistic black holes have very, very, very small temperatures, which we've never actually experimentally detected. But in principle, just for effect, I've exaggerated it to show you how Hawking radiation changes the picture that we have of a black hole. Okay, so as I said, you can compute not only the temperature, you can in fact compute the spectrum, and the entire spectrum is what's called a black body spectrum. And it is of this kind. So here you see a spectrum of two different black holes at different temperatures, and it will obey this kind of a Planck law. Okay, so now let's say you believe this fact that black holes have a certain temperature. Then you can just use high school physics to calculate some more consequences. You see, you know that the energy in the black hole is just the mass in units where C is 1, or it's mc squared. And what I just told you is that the black hole tends to lose energy through radiation. So the rate of loss of energy, you see, is if you have some object which has some temperature, you know that it loses energy by the Stephen-Boltzmann law. And the Stephen-Boltzmann law is just that the rate of loss of energy is sigma t to the power 4 into the area. Now in the black hole, you have gray body factors and so on, and so these things, some constants and so on get modified. But this is a reasonable way to understand the fact that as a result of the fact that the black hole has temperature and the conservation of energy, since the black hole is emitting radiation, it must be the case that the black hole at the same time is becoming smaller. Now, if this is the case, this tells you that the rate of change of mass is just given by 1 over the mass square. If you just put in the formula as I showed you for the Schwarzschild radius, and you calculate the area and for the temperature. And so you'll find that the rate of change of the mass goes like 1 over m squared times some constant, which you see on the slide in front of you. But what this tells you is that if you wait for a long enough time, and that long enough time is proportional to the cube of the initial mass of the black hole, then the black hole evaporates away entirely. So you start with a black hole, and if you wait for a long enough time, then the fact that you have Hawking radiation leads you inexorably to the conclusion that if you take a black hole and you do not disturb it, it will evaporate away completely after some time, in a time that's proportional to the cube of the initial mass. Okay. Now, I should warn you that astrophysical black holes, or the black hole in the center of our galaxy, is never going to evaporate in our lifetime, and it's not even going to evaporate in the lifetime of the universe. Because if you take a solar mass black hole, the lifetime of a solar mass black hole, if you compute what I said previously, is 10 to the 67 years, and that's much longer than the age of the universe, if you know of. So solar mass black holes and astrophysical black holes and all the black holes that we have actually seen around us are effectively eternal black holes. Okay, so this evaporation process is irrelevant for them. On the other hand, there's nothing that prevents the formation of a black hole that's much smaller than these black holes. So in principle, you could take a black hole which was, say, a few hundred tons, okay, so the mass of a large plane. And if you took a black hole of that size, then you could compute its lifetime would be 5 seconds. So if in principle you had a way of forming black holes, maybe through astrophysical processes or through sufficiently advanced technology, then such black holes would evaporate pretty fast and would evaporate even over human timescales. And so it is not that all black holes necessarily evaporate over a long time, but it is true that for solar mass black holes, the effects, or for astrophysical black holes, the effects that I described previously are not relevant. But theoretically, they are relevant because you could have black holes of other masses of the kind that I've shown here. Okay, so now we are coming to the paradox, because you see, look at what the process I have described tells you. It tells you that if you have some black hole that formed in some way, it would form. So let's say you had a star, and the star led to a black hole. And after some time, the black hole would evaporate away entirely. And so what you would be left with would just be thermal radiation. And so the process of black hole formation and evaporation that I have described to you looks like what it is on this slide. Okay? But if you think about this carefully, you see this is kind of funny, because it suggests that you could start with one star which was made up of more hydrogen and less helium, and maybe another star which was made up of more helium and less hydrogen. And both of them could form a black hole of the same mass. And I described to you that the temperature of the black hole was just proportional to the inverse mass. And therefore, it would seem that if you believe this process, the final radiation that would come out of both black holes would be the same in both cases, even though the stars to start with were not the same. And this was the argument that Hawking made. Hawking argued that these time evolution arrows would not be reversed in this process of black hole formation and evaporation, and that is called the information paradox. It is a paradox because the fact that time evolution should be reversible is a very fundamental facet of both classical and quantum physics. If you think about what you learn when you first learn physics, people teach you how to calculate ballistic trajectories. So you might have problems in the exam saying, if you throw a ball with some force and some initial velocity, where will the ball land? And you can calculate that. But in fact, there is something else you can do. If I tell you the final velocity and position of the ball, you can also compute the initial velocity and the initial position of the ball. So you can always solve the equations of physics either forward in time or backward in time. And that's just a fact, comes from the Newton's law, which is written in this way. It tells you dp by dt is f of px. You can solve it for positive t or for negative t. And there is nothing privileged about being able to solve it for positive t. And in fact, when people do these ballistics reconstructions at crime scenes, which at least of the kind that I see in movies or you hear about in books, this is precisely what they're doing, right? They're trying to see, the bullet was here, so where was it fired from? And that's an example of how you do an evolution back in time. You can, of course, compute if the bullet is fired, where it will end up. But given where the bullet has ended up, you can also compute where it was fired from. And so reversibility is a property of classical dynamics. It is also a property of quantum dynamics. If you look at quantum mechanics also has the property that time evolution is reversible. And that's a property of the Schrodinger equation, which tells you that the wave function, the rate of change of the wave function, is given by taking the Hamiltonian operator and acting on it with the wave function. But you can solve this differential equation forward in time or backward in time. And so it is always the case that in quantum mechanics and in classical mechanics and in all aspects of physics that we know, information is always preserved. You never have a situation where you can evolve forward in time but not evolve backward in time. And therefore, the process that I showed you previously is a paradox, and that is what is called the information paradox. Okay? The fact that it looks, Hawking argued that in the case of black holes, this could not be done. Okay, so let me try and immediately tell you something which we've understood actually for a fair amount of time, and then I'll discuss more recent developments. So you see, the point is that Hawking argued that you take a black hole and you'd form radiation. So let's say this was the final state of the radiation. And Hawking said that, this is a cartoon, by the way. So what I'm showing you right now is not some realistic simulation of radiation. It's just a cartoon to make a point which I'm now going to make. So Hawking said, look, you could take a black hole and you would emit some random spectrum of radiation, which would have some distribution. So, you might emit like photons of different colors, yellow photons, blue photons, red photons, other particles, and they would all be emitted randomly with only some probabilistic distribution. So you could predict how many red photons there were compared to how many yellow photons, but this would basically be the same, whatever the initial state of the black hole was. But in fact, we know that this is not quite how information is stored, even other systems. Even if you take a black body and you allow the black body to emit radiation, the black body does something pretty similar. It emits radiation at a certain spectrum, and so it would emit photons of this kind. And it is true that the spectrum of photons is there's some probabilistic distribution of the photons that are emitted, but in fact, the information that is present in the final set of photons that are emitted is not only in counting the number of red and blue and yellow photons, which might indeed be the same for different black holes with different initial states, but also in the correlations that exist between the emitted photons. So you might have some final state that looks like, some of its properties are the same as another final state, but that might nevertheless have correlations which are visible to more fine-grained observations. In this example, it might look like there are just some photons which I've drawn at random, but if you look more closely, you will see here that if you take a yellow photon and you take you draw a line to this black ball and you go to the other side, you will find on the other side a purple photon, and if you take a red photon and you draw a line here exactly on the other side, you will find a blue photon. So at first sight, it might have looked to some of you, unless you're very good at pattern recognition, that this was just a random distribution of dots. But in fact, this random distribution of dots has more fine-grained information, which is visible if you look at it more closely. This is an example of something that happens often in statistical mechanics, where you might have correlations between different observables that have more information than the observables themselves. So if you just measure the temperature at some point in the room and the temperature at some other point in the room, that gives you some information. But if you start measuring also the correlations between the temperature here and the temperature somewhere else, that gives you more information than just the initial amount of information you had in measurements of the temperature. And in fact, one can show, many people have argued, including us, that these correlations, if you want to preserve information, can be as small as e to the minus SBH, whereas SBH is the entropy of the black hole that I introduced earlier, which is the area of the black hole. And this entropy of the black hole can be very large. This is what the entropy looks like. It's proportional to the square of the mass. For a black hole of the size of the sun, this entropy would be 10 to the power 77. So even if you had very, very small correlations between the final photons that were emitted by the black hole, those would be sufficient to preserve information. Okay? And so there is an error in Hawking's argument, and the error in Hawking's argument that there is a paradox is that it neglected the importance of these exponentially small corrections. So Hawking was making a certain argument that came from gravity and putting together gravity and quantum mechanics, but we have now better understanding of how quantum statistical mechanics works, and it tells us that information can be preserved even in terms of these delicate correlations, and Hawking did not rule them out, and in fact could not have, his calculation was not precise enough to rule them out, and therefore the calculation that Hawking performed did not really lead to a paradox, because all it suggested was that to first approximation, if you look at the spectrum of particles that is emitted, the spectrum of particles that will be emitted will look like that of a black body, and it will be similar for black holes of the same mass. But it did not account for the fact that you could store information in correlations between the spectrum of the final spectrum of particles that is emitted. So that is a first order resolution to the information paradox that I think we understand quite well. Now, however, there are some more questions one can ask. You see, I said that the way information is preserved is in correlations in this final radiation. But you see, the point is that if you think a little bit more about the processes that I showed you previously about how Hawking radiation forms, it looks like this radiation emerges from the horizon, and the horizon seems to be free of information, because it seems like the mass which formed the black hole, the object which formed the black hole, the star which formed the black hole, very soon leaves the vicinity of the horizon and falls into the singularity. And I tried to explain to you earlier that this radiation was coming from near the horizon. And so you might still ask, well, you're telling me that the way information is preserved is in terms of this correlations in these Hawking quanta, but how are even these small correlations formed, given that there is nothing near the horizon, given that the horizon just seems like it's empty space? Okay? So you can ask going beyond the original question that Hawking asked, and this is something you should keep in mind when you think of the information paradox. The information paradox is not one paradox, but rather it's a series of questions one can ask about black hole evaporation. And the first order question that Hawking asked was, look, it looks like black hole evaporation is not reversible. And there's an answer to that question, which is that, look, it is reversible because information is stored in these delicate correlations. But then you come up with a second order question, which is, how are these correlations formed? What is the mechanism that gives rise to these correlations? So in fact, over the past year, there has been some work on trying to understand this. This is a work that perhaps some of you have heard of. There's been some popular description of this work. And this work has used a particular kind of model of black holes, where you take a black hole in the middle and you couple it to a region which has no gravity. And many people have made, including the authors listed here, Pennington, Almeri, Mahajan, Maldacena, Hartman, many others, have made progress in trying to understand in this kind of a setup how these correlations form in these kinds of models, where you take a black hole and at some point you couple it to some auxiliary system that does not have gravity. In fact, in this talk, for the rest of the talk, I don't want to describe this model because some of us, including work done by me and many other collaborators, we've pointed out that perhaps this kind of a model, which has been used very commonly in the recent literature, is not realistic. And that is because this kind of a model assumes that you have a black hole which is coupled to an auxiliary system. But in fact, in the real world, if you were to form a black hole of the kind I mentioned, even if it was a small black hole, it would never happen that gravity entirely switches off. And so we have described a different mechanism for how these correlations emerge, which is valid for situations where gravity is dynamical throughout, which leads to slightly different answers from the situation where gravity is switched off entirely. And so I'm going to try and describe this model of how these correlations form when gravity is dynamical throughout. This is not to say these models are wrong. These models are right, but they're not directly relevant for realistic black holes, we think. And so I'm going to try and describe to you the physics that we think is relevant for more realistic black holes, where gravity is dynamical throughout. Okay, so let me try and explain in as simple language as I can. Okay, so the basic point I'm going to try and make to you now is that information in gravity, so before I show you pictures, the basic point I'm going to try and make to you in the last few minutes of this talk is that information in gravity is stored very differently from the way information is stored in non-gravitational theories. Okay, so that's the punchline of the next few slides I'm going to give you. Let me try and explain this as simply as I can. First, let me remind those of you who know quantum mechanics about the form that energy eigenstates take in quantum mechanics. Okay, so remember, the first thing that we learn in quantum mechanics is that there's an uncertainty principle. The uncertainty principle tells us that if you try and localize the position of an object, you get a large uncertainty in its momentum. And alternately, you can think that you also get a large uncertainty in its energy. Alternately, if you try and fix its energy, so you try and think of something which has an exactly fixed energy, an energy eigenstate is always delocalized in quantum mechanics. Okay? So an energy eigenstate is a delocalized state in quantum mechanics, whereas something that's localized cannot be an energy eigenstate. So this is just a feature of basic quantum mechanics. It comes from the Heisenberg uncertainty principle. Good. Now let me tell you something that's special to gravity. Okay, so this is something that's special to quantum mechanics. Now I'm going to tell you something that's special to gravity. So what is special to gravity? Well, in gravity, there is a special property of energy, which is that energy obeys a Gauss law. In gravity, the energy can be measured from far away. You know, we know the mass of the sun, right? But none of us has ever been to the sun. No human has ever been to the sun, but we still know what the mass of the sun is. And the way we know the mass of the sun is because we can measure its energy from far away using the gravitational attraction of the sun. And that in fact follows from something that we learned that's very basic about gravity, which is the Gauss law. So in gravity, there is a Gauss law which tells us that the energy can be measured from infinity. Okay? So energy has a special feature in gravity, which is you don't actually have to go locally to measure the energy, you can measure the energy far away. But now think of what happens if you put together the uncertainty principle I told you and the fact that there is a Gauss law in gravity. Okay? You see, let's say, how do you localize objects in quantum mechanics? In quantum mechanics, the way you would localize objects is you take a superposition of energy eigenstates. Right? You try and superpose different energy eigenstates the same way you superpose waves. And by doing that, you get some object which is localized at one spot. Okay? So it's a superposition of different energy eigenstates. But in gravity, I told you that you can measure the energy from far away. So you see, if you try and superpose, let's say you have some matter and you try and superpose its energy eigenstates to form this localized blue ball. But now in gravity, you're in trouble because when each of these energy eigenstates, which is say some eigenstate of this matter which has some energy, also has a correlate which is the metric that is far away, which is also modified according to its energy. Right? So if you try and superpose it, if you did not have this right-hand side, if you did not have the metric part, then you would have been able to construct a localized object as we do usually. But in the presence of the metric, you're never able to have exactly destructive interference everywhere else because the metric always tells you about the energy. So just to say once more, the way you construct localized excitations in quantum mechanics is by making sure you have constructive interference in one region and destructive interference elsewhere. When you add the gravitational degrees of freedom, since the energy itself is something which can be measured far away, you're unable to have destructive interference outside one region while having constructive interference only in one region. And so the joint probability distribution of the metric with other dynamical fields allows you, in fact, in a theory of quantum gravity, to identify information from far away. So just like you can tell the energy even in classical gravity from far away, in quantum gravity has the property that you can in fact identify the state of a system by making measurements far away, by measuring the joint probability distribution of matter fields and the metric fields. Now, if you apply this principle, so this principle is what we have called the principle of holography of information. And what the principle of holography of information states is that if in gravity you have a slice, so you take a spatial slice, so you take some region of space, then the information that is available on that slice, say in this blue region in the slice, is also available near the boundary of the slice, which is in these red regions. So in quantum gravity, information is stored very differently from the way information is stored in ordinary quantum field theories, in that in ordinary quantum field theories, information is localized, but in quantum gravity, information is delocalized in this unusual way, in that the information that's available at one point is also available in a set of observables around that point. And this is called the principle of holography of information, which we have developed over the past few years. Okay, so now if you apply this principle to black holes, you see, what would you find? The holography of information tells us that the region outside the black hole always retains a complete copy of the information that has fallen into the black hole. And therefore, information is not lost. And this also tells you how these correlations form in Hawking quanta, because it tells you that the horizon, even though it looks like the matter has fallen away from the horizon, there is always information that is available near the horizon. And that is the mechanism. So not only is it the case that information is not lost because you have these small correlations between final Hawking quanta, but in fact, you also now have a dynamical mechanism for understanding how the information is not lost. And that comes through this principle of holography of information. Okay, so just to summarize, the resolution that I think we're understanding better and better to the information paradox is that there are two errors in Hawking's argument. The first error I already emphasized, which is that Hawking argued that you had these simple observables, which were basically the temperature that you could measure far away, which looked thermal, and he argued based on that black hole formation and evaporation was not a reversible process. But there's an error in that because small correlations can preserve information about the initial state. But the second point, which we have learned, which is something we have learned more recently about quantum gravity, is that quantum gravity localizes information very differently from classical gravity and from non-gravitational theories. And that comes by putting together this uncertainty principle in quantum mechanics and the Gauss law in gravity. Of course, there's more work that you have to do to try and prove it in a more careful way, but the basic physics just comes from these two. And this tells you that not only is it that you have these correlations which preserve information, it also tells you how those correlations are formed. Okay, so let me conclude with some philosophical points. You see, I told you in the beginning that in general relativity, you had a fabric of space-time, right? So now how should you think of this picture where in some sense information is also available near the boundary of the space-time? We don't actually have very good pictures, but one picture that people sometimes draw is this picture of threads of space-time, which suggests that the amount of information in the region is not given by the volume of the region, but its area. In this picture, the amount of information in these threads, the number of threads, is determined by the perimeter of this region and not by the area itself. And so maybe the way you should think of space-time is not in terms of a continuous fabric which can store independent pieces of information everywhere, but rather in terms of something more subtle, in terms of something like the threads of space-time. And I think this is very interesting, in some sense it's the reason we study these topics, because it is not only, it's kind of giving us a new philosophical way of thinking about space-time. So, we started with Newton's laws, which had action at a distance. And then we said, we don't like that because, we don't like non-locality. And so we invented this fabric of space-time and came up with some local theory of general relativity. And then we put together quantum mechanics and we found this paradox and we thought more about it. And now we find that, maybe we should think about space-time in a more subtle way, not in terms of this fabric of space-time, but rather in terms of, these threads of space-time, which kind of gives us, takes us a little bit back towards this non-local description. Of course, not all the way back, but, takes us away from this exactly local description that was at the heart of general relativity. So I think it's interesting that there's this progression of perspectives on gravity and space-time, which is one, some philosophical lesson we learn about the world from us by thinking about black holes and all of this physics. Okay, so that's all I wanted to say. I think I'll stop here and we can take questions if there are some.
Can you hear me? Hello, am I audible?
Yeah.
Yeah, hi Suvrat. It's a nice talk.
Yeah.
So this last point, this physics, Newton physics was non-local.
Yes.
And then Einstein make is local, and then finally some sort of non-locality again we are seeing.
Mm-hmm.
But this fact, can we see at least in EPR paradox, if we consider these two singlets specially separated, if I do something on one part, of course, there is due to this correlation, due to this peculiar entangled correlation, something is there. But of course, that non-locality is completely different from Newtonian's non-locality because we cannot do faster than light signal. But my point is this non-locality even in standard quantum mechanics, isn't it very evident from EPR paradox and particularly from Bell's experiment?
No, it's different because of what you just said. In the situation where you have an EPR paradox, you can do unitary operations there's no paradox when you have EPR pairs, entangled pairs. You can do unitary operations on one pair in such a way that it's entirely invisible to the other pair.
No, but if I do a measurement,
yeah, you can of course you can do a measurement. You can take one pair and you can entangle it with something else. But as you just said, there's no transmission of information faster than the speed of light, and you can prepare one qubit in a way that's entirely separate from another qubit. So you can act with unitary operations on one qubit. In this situation, what is happening is somewhat different. The thing that is being said is that you really need to identify the degrees of freedom. When you have these two qubits, one qubit is 1 degree of freedom and the other qubit is another degree of freedom. In this situation, what is happening is that you really need to identify a degree of freedom at one point with a combination of degrees of freedom far away. So there is, it is not that there are independent degrees of freedom which happen to be correlated. It is really that you need to identify a degree of freedom that lives at one point with a degree of freedom with some combination of degrees of freedom that live on the boundary of the space. So it's a different kind of, it's really in some sense a loss of locality. There is no actual loss of locality that's involved with ordinary entanglement, which of course happens all the time in quantum mechanics and quantum field theories. And it's also true, of course, that observations in quantum field theories commute at space-like separation. In gravity, that is not the case. And so it is really a loss of degrees of freedom. It's not that degrees of freedom are correlated. It's that degrees of freedom are the same. They're identified. So when you have two qubits, the two qubits are different. They may be correlated, but they're distinct qubits. But here the statement is that a qubit that lives here is the same as a qubit that lives on the surface of the room. So if I do something to the qubit, or if I measure that qubit, I also measure this qubit. And or if I make some unitary operation to the qubit on the surface of the room, I simultaneously make the same operation to this qubit that lives in the middle because they really are identified. So it's very different physics from entanglement. It's
just another technical point, since I am not very expert in this when you say correlation, how it is measured in this here?
So I said it was more than correlation. In the case of entanglement,
not this one. This earlier, this you said no. This Hawking radiation can be exponential something some correlation factor.
It is a question of in-point correlators. So if you have some, I think I said here. More technically, if you look at the metric observables at some point, you have to look at in-point correlation functions of the metric or end-point correlation functions of the particles that are emitted. So you might have a gauge field of photons that are emitted, and you have to look at correlation functions of many photons that are inserted, and then in those correlation functions, you have to look at terms that are exponentially small.
My question is, let me ask this: if we have two classical variables x and y, we say they are correlated means some quantity that is mutual information. Here, mathematically what quantity is?
It is the same. It is the same. Of course, in quantum mechanics, there are Bell inequalities that classical correlations can't disobey, and quantum mechanical correlations do disobey, but it is still a correlation function. So it's a quantum mechanical correlation function, but it is still a correlation function.
Okay, sure. Thank you.
Yeah, sir, we have some questions in the chat box.
Sure.
So I can read it out for you.
Yeah, that'll be great because I can't see the chat.
Yeah.
I don't know why I can't see the chat.
Yeah. Subrabalan M asks that, is holography specific to black holes? Does holography imply that information about any part of the universe is available at every other point?
So it doesn't imply that information about any part is available at every other part. Holography of information as we've been formulating it is a statement that information about so it's not special to black holes. That's a good question. But the information about some region is available on the boundary. So information about what's happening in the middle of the room is available by joint observations on the surface of the room. So the physical way you have to think of it is you have to surround a point with observables, and then you can determine what's happening in the point itself. So it is not that information at this point is the same as information at some other point. Okay, but rather information at one point can be obtained by making measurements around the point, everywhere around the point. And this is not special to black holes. The argument I gave you using just quantum mechanics and the uncertainty principle and the Gauss law did not rely on black holes. So it applies to black holes, but it is something which is independent of black holes. Also applies to black holes.
Yeah, there is another question by Leela Ganesh Lakkaraju. It says that initially it was thought radiation is a thermalized state with completely mixed state. The resolution of this comes from the fact that thermalized state is wrongly identified because it is essentially a many-body localized phase because the quantum state is non-trivially tensor product energy and metric. Am I right in this assumption?
Can you say the last part again? Quantum state is what?
Yeah, it says The resolution of this comes from the fact that the thermalized state is wrongly identified because it is essentially a many-body localized phase, because the quantum state is non-trivially a tensor product of energy and metric.
Yeah, it's not a tensor product, it's an entangled state, and many-body localization is a slightly different phenomena. But roughly, I think that the point is correct that initially Hawking argued that the state is a mixed state. But the point is that pure states can look a lot like mixed states. If you take a pure state in a Hilbert space which is large enough, it can mimic a mixed state to exponential accuracy. And so the mixed state, it is indeed correct that the final state was incorrectly identified as a mixed state. It is actually a pure state in a complicated large Hilbert space.
Hello. I have
a question. Go on, yeah.
Yeah, so you said that there are some small correlations of the degrees of freedom which are emitted from the black hole.
Right.
So I have read that the degrees of freedom of a black hole are strongly interacting with all the other degrees of freedom in the black hole. So I would expect that the degrees of freedom which are emitted would also be strongly coupled with each other. So what exactly do you mean by small correlations here?
No, they're not strongly coupled with each other. You know, if you take a black hole which is big enough and you emit like particles, the correlation between them are small. These correlations, the black hole radiation is thermal to first approximation as Hawking computed. So it's not true that, you know, some photon which is emitted from one side of the horizon is strongly coupled with the photon that's emitted from the other side of the horizon. You can take a black hole which is large enough, and then these correlations are indeed small. So I'm not sure what you're referring to when you say, you know, it depends on, when you say degrees of freedom are strongly coupled or weakly coupled, it depends on what are the degrees of freedom you use to describe the theory. So maybe what you're referring to is the fact that there is a description of black holes in terms of some strongly coupled degrees of freedom in some models of what is called the ADS-CFT correspondence. But, you know, in terms of the ordinary, the space-time degrees of freedom, which is that there's a metric which is fluctuating and so on, that's a weakly coupled description when we usually talk about it. There's no problem.
Okay, I understand.
So there is another question in the chat box. I'll read it out.
Yeah.
So it says, it's from Karan Singh. It says, sir, according to the second law of black holes, as you said, the area always increases. What exactly do you mean by the area of the black hole? As you said, the region within the Schwarzschild radius isn't ordinary.
Oh yeah, but you can still define an area of the black hole. You see, I didn't try and define a volume of the black hole. The volume of the black hole would be hard to define, but the area of the black hole is not something which is, the area of the black hole is a well-defined object. So you have a horizon, the horizon is at a particular value of r, and you can talk about the area of the two sphere, that value of r. You're right that, you know, talking about the volume of the black hole is a more complicated thing to do. But the area of the black hole is well-defined.
Yeah, we have an. It says radiation. One particle goes to singularity and the other comes outside.
Yeah.
So can we conclude that the black holes evaporate since we initially started with a particle going in and another moving outwards?
Right. Correct. So black holes do evaporate. That was the basis of the paradox. Now, the paradox was that as a result of this virtual pair production, black holes evaporate, and because one particle goes out and the other particle falls in, and so black holes evaporate. And then the whole point was, it looks like from black hole evaporation, information is not preserved. And so the paradox was, how does this happen? Because this is in conflict with reversibility. And then I tried to explain various resolutions.
Yeah, thank you, sir. Any more questions from the audience?
Can I ask one more, Suvrat?
Yeah, sure. Yeah.
So this little bit is again philosophical question. So we generally take this stand that in a finite region, a finite space-time region, we can store finite amount of information, and our computer has some computing power. Now, you see, if information at one point can be accessed to another point instantaneously, then actually I don't require finite place to store information because everything is accessible to me now instantaneously. So your proposal, what do you think that it has implication in computational power or complexity theory?
None, because in terms of the computer, if I have the hard disk, it is true that in some sense the proposal is valid in that if I make measurements in the computer in front of me, I can determine what's happening in the hard disk. But to do that, I have to use Planck scale measurements. This information is stored in Planck scale fluctuations of the metric around the hard disk. So not only do I have to measure classical fluctuations, which is already very hard to do, classical gravity waves that are emitted, I actually have to measure quantum fluctuations. So in terms of actual computational things, this is not relevant. Second, it is not that information is propagating instantaneously. It's rather that if you prepare a state of the hard disk, you simultaneously have to prepare a state of the space-time around it. So it's that the constraints of gravity are so strong that the space of the hard disk is also imprinted in the constraints of the space-time around it. But of course, in terms of actual quantum computation or so on, it's not relevant because these effects are extremely small. They're relevant for black hole evaporation because there we are talking about these delicate effects, but not for quantum computation. It's not that information is traveling faster than the speed of light, but rather it's that the space-time is constrained in such a way that if you prepare the inside of the space-time in some way, you have to also prepare the outside in a certain way.
Okay. Thanks so much.
Any more questions? Yeah, so if there are no more questions, thank you, sir. It was a wonderful session and a very insightful session. Thank you for accepting our request. And
Ravi, there is a question, I think, in the chat box. Maybe I can read it out.
Is there a question?
Okay. There's a question which is, I think, a continuation of the question by Karan Singh. So it says the dA greater than 0. I think it means area increasing is also another contradiction to black hole paradox. That is, when it evaporates, area reduces.
No, that is not a contradiction actually. That's this area larger than 0 is a classical law. In the presence of quantum mechanics, this law does not hold. There is a sense in which a generalized second law holds, which is that the entropy of the black hole plus the entropy of the radiation always increases. But this fact that dA is larger than 0 is a classical law, and in quantum mechanics, it's well understood that just does not. You have to modify it and replace it with a generalized second law, which is not violated during black hole evaporation. Great. Okay.
Yeah. Thank you, sir, for being with us here and for delivering this wonderful lecture. Thank you.
Thank you. Okay. See you then.